All right, so with this unit, we're going to shift into a different way to start drawing conclusions based on the data that we get. So we're still going to have some claimed values. You're still going to have samples that have been taken, but now as opposed to creating intervals and comparing the values within the interval to a claimed value, we're going to start using something called hypothesis testing. And this is going to be it's going to be based on probabilities. And we've done this before when you guys were doing some of the stuff in a couple units ago. What's the likelihood of getting 8 out of the 10 fish being a certain length? You went and you did a z-score and a probability statement and all that stuff. It's essentially it's the same idea here, just a little bit different methodology. So the first thing you're going to do when you're going to start doing these tests is you're going to write the name of the test and the conditions. Right? We did this with intervals. You wrote down, oh, this is a 2-prop z interval. This is a 1-sample z interval. This is a 2-sample t interval. You wrote that down, and then we came over here to conditions. This particular page, we're going to talk about means. Remember the 2 conditions for means, and we're just going to do one at a time right now. We want random. A lot of times we just wrote SRS, and then we either want large, so n is greater than 30, or we wanted it to be normal. Right? Now, once we did the name and the conditions, we're going to write our hypotheses. Now, the thing is, a hypothesis, it will always use a parameter. And remember, a parameter describes the population. So the 2 parameters that we're most likely going to use are mu and p, right? There's for means and the p for proportions, right? A lot of our intervals were based on x bar, which was for means, but it was a sample mean. Mu is the claimed population mean, and then our intervals with proportions were based on p hat. Now we're going to base it on p, the population proportion. The other thing when you're writing the hypotheses, equality goes with your null hypothesis. So what that might look like for us, if we come over here, the null hypothesis, HO, versus an alternative. What you're going to do is either going to be mu or p that goes into this first box. And then that last box for us right now is going to contain some number. And that same number is going to go in both boxes at the end. In between, equality always goes with the null. And I'm actually going to clean that up just a little bit so it's easier to read. Equality always goes with the null. So in other words, the null is always either going to be equals, greater than or equal to, less than or equal to, which means the alternative is not equal, greater than, or less than. For step 3, we get into the mechanics of this thing. So the first thing that we're going to do is you're going to get your test statistic. And we've done this before. For us, this was a z. Or when we started doing some of these, a t-value. That's when you found your z-score, found your t-score, whatever that might be. Those are what are called test statistics, remember. And then we're going to get a p-value. And what that p-value is, we'll talk about it here a little bit more in just a second. Actually, if we come down to that box right below what you're looking at, well, what is this p-value? A p-value is the probability of obtaining a certain outcome or something that's more extreme. We did this already. But the big thing about this is we have to base this probability on the assumption that we should have gotten whatever the null hypothesis told us. So if you think back about some of the card examples, all the probabilities, of getting 3 red cards or 4 red cards in a row were based on the assumption that a deck of cards has half red, half black, right? So the example we did in class, when we got to about the 4th or 5th card, that probability got so small, right, 0.5 to the 5th, that that we no longer thought the original hypothesis of an equal deck was true. Um, so back out of the mechanics, after you get a p-value, you then decide whether you're going to reject or fail to reject. And what you're going to do, this you're going to do this, you're going to compare your p-value to an alpha level. And the typical alpha level that we use is 0.05. So not going to make a lot of sense just on the surface, but if we get this down now, as we do some examples over the next few days and the next video or so, you're going to start to see how this works. So our probability cutoff level is basically 5%. So if there's a 5% chance or smaller that we get certain results, then we would then reject the null, right? So we never actually accept anything. We either going to reject the null or fail to reject the null. And then finally, we're going to throw our answer into context, right? So that is nothing new to us. Keep it in mind as you do some of these. When do I use t versus z? Remember, t goes with sample standard deviation, and then z goes with population standard deviation. So a couple quick examples on this particular sheet, and I'll switch over using some of this stuff. If you'll let me kind of go back, you're going to see problems a lot like we saw with the confidence intervals, but this time we're going to set up tests. So this doesn't look all that unfamiliar. In Illinois, a random sample of 85 8th grade students had a mean score of 282 with a standard deviation of 35. The test results prompt a state school administrator to clear the mean score, so you can see it's in red for a reason, that their average score was more than 275. So the first thing that we want to do when we start thinking about our box, if you will, is are we talking about which parameter, mu or p? Well, there's the word mean. That means we're talking about mu. So now we need to just go ahead and start translating. I see the word more than sitting there. More than 275. Well, that's greater than 275. Well, what we should have seen before, right? So if they're claiming it's more than 275, then that means the state average is 275. So the null hypothesis here would be that mu is equal to 275 versus the alternative that it's greater than 275. So we take a look at the second example. Manufacture a sprinkler system. They're claiming that the average, right, here it is in red again, the average activating temperature. So right away we could go ahead, the null hypothesis, right? So we have our box, then our next box for the number, and then HA. Let's excuse me if I'm having to do this by hand. That first box, is it going to be a mean or a proportion here? And so for us, that's average, which means these are both going to be mu. So go ahead and put that number there. And they're going to claim that the activating temperature is at least 135. Well, at least means greater than or equal to. So greater than or equal to always goes with a null. So at least 135. And then the alternative, right, if that's not going to be true, if we're going to reject that, then what that tells us is the alternative to greater than or equal to is less than. What you should notice is the number in the second box always going to be the same numbers, right? Let's take a look at another example. A nutritionist claims that the average tuna consumption or mean tuna consumption, so here we go again, there's mu going in the first box. The alternative, start with mu, is 3.1. So that's equals. Equals goes with the null. Since 3.1's in that box, go ahead and put 3.1 here for the other one. All right. Is there evidence to support the nutritionist claim? Well, here there's no indication of the less than, greater than. So what we're going to do is just use not equal to. All right. One more example. Company claims that 3 out of every 100 people in this small town are affected. So in that first box, you don't have to have the box if you don't want to. This is a proportion, 3 out of 100. So we got a P, we have a P. 3 out of 100. That's the claimed true proportion. So we can go ahead and put 0.03 in the second box for both of these. So again, apologies for being so rough. So they claim that the average is, right? 3 out of 100. So the P is 0.03. After this random sample is taken, we're wondering, is there evidence that is affecting more people? Here we have an indication there's more, so we can use greater than. So the next video is going to start working through some of the examples for this, but there's just kind of your setup of how to get this thing going.